Hello! Today we are going to tackle a challenging problem from the 2006 International Mathematical Olympiad shortlist. Our goal is to find all pairs of integers x and y that satisfy this exponential equation. At first glance, this looks like a Diophantine equation involving powers of 2. Since y squared is on one side, we are essentially looking for when this specific sum of powers of 2 results in a perfect square. Note that because y is squared, if a pair x and y works, then x and negative y will also work. We will focus on finding non-negative values for y first. Today we're going to solve an interesting problem from the 2006 IMO. Determine all pairs of integers x and y such that 1 plus 2 to the x plus 2 to the 2x plus 1 equals y squared. Let's begin by considering the possible values for x. If x is a negative integer, say x equals negative k where k is positive, then 2 to the x becomes 1 over 2 to the k. This would result in a fraction on the left side. Since the right side is an integer squared, the left side must also be an integer. For any positive integer k, these fractional terms cannot sum up with 1 to form an integer. Therefore, x cannot be negative. We only need to consider x as a non-negative integer. Let's check the simplest case where x equals 0. Plugging x equals 0 into our equation, we get 1 plus 1 plus 2. This gives us 4, which is a perfect square. So for x equals 0, y can be 2 or negative 2. We found our first two pairs. Now, let's look for solutions when x is greater than 0. When x is positive, the left side is clearly greater than 1, so y cannot be 0. Let's rearrange the equation to isolate the powers of 2 on one side. Subtracting 1 from both sides, we get 2 to the x plus 2 to the 2x plus 1 equals y squared minus 1. The right side is a difference of squares, which factors into y minus 1 times y plus 1. Notice that y minus 1 and y plus 1 are 2 units apart. Because their product is even, both factors must be even. This implies that y must be an odd integer. If we let y equal 2k plus 1, then y minus 1 is 2k and y plus 1 is 2k plus 2. This leads to 2 to the x times the quantity, 1 plus 2 to the x plus 1, equals 4k times k plus 1. If we quickly check x equals 1, the sum is 11, which is not a square. So x must be greater than or equal to 2. Let's refine our analysis for x greater than or equal to 2. The greatest common divisor of y minus 1 and y plus 1 is 2, because they are consecutive even numbers. This means that in the product on the right, one factor must be 2 to the x minus 1 times some odd number, and the other is 2 times some other odd number. Wait, if x is large, we can be more precise. Let's try x equals 3. What about x equals 4? 529 is 23 squared. This gives us more solutions. When x is 4, y can be 23 or negative 23. To prove if there are any other solutions, let's go back to our factored form. Let's assume y plus or minus 1 equals 2 to the x minus 1 times an odd integer k. Substituting this into our equation and rearranging, we get 2 to the x minus 2 times the quantity k squared minus 8 equals 1 plus or minus k. If we take the plus sign and k is greater than 1, there is no solution. If we take the minus sign and k equals 3, we find x minus 2 equals 2, so x equals 4. For any k larger than 3, the left side grows much faster than the right side, so there are no further solutions. We have now systematically checked all possibilities for x. First, for x less than 0, there are no integer solutions. For x equals 0, y is plus or minus 2. Checking 1, 2, and 3 yielded nothing, but for x equals 4, y is plus or minus 23. Finally, we proved no solutions exist for x greater than 4. The only integer pairs, x, y, that satisfy the equation are 0, 2, 0, minus 2, 4, 23, and 4, minus 23. You've seen how to use parity, divisibility, and bounds to solve an IMO level problem. Great work today!